Today we're going to illustrate the concepts of mean, variance, covariance, correlation, and diversification. I hope to do this in an intuitive manner. Okay, so suppose that we have an asset that exhibits certain form of returns over a course of say 5 days, or rather I say 5 periods. So period 1, period 2, period 3, period 4, period 5. So assuming that, okay, so this is period, this is returns. Suppose that this asset has, say, positive return on day 1, more returns on day 2, and it exhibits a loss on day 3, exhibits a slight return on day 4, slight loss on day 5. So assuming on average it returns us 4%. Okay, so we can say that the mean of the return over the 4 days is 4%. The formula is given by is equal to the summation of the returns over the I number of days, 1, 2, 3, 4, 5, divided by number of days n. So this is n, is I equal 1. Okay, so mean is very straightforward. So let me add a bit of complexity into this picture, assuming that we have another asset that has such returns form. So we have here, here, and a very drastic drop here, here, and maybe here. Okay, so the second asset has this kind of returns over the 5 days, and assuming that the mean is also 4%, can we say that these two assets are comparable and they have the same risk structure? Apparently not, because second asset has clearly a more risky profile. Assuming that you invest in a second asset at this point in time, and you will be making, say, a huge profit over the course of 1 period. Assuming that you invest in this asset at this point in time, you'll be making a huge loss over 1 period. So as you can see, there's a huge risk for this second asset. So the question is, clearly these two assets are not comparable, and we need a way to measure the riskiness of these two assets. That's where the variance comes in. So intuitively, you can think of variance as the distance between the asset and the mean, the asset return on each day and the mean. Okay, so let's look at the second asset. If we sum up all the difference between the asset return and the mean for each day, we may get something like something close to 0, because there's a positive part here and there's a negative part here. So if we sum up all the positives and negatives, we may get something that is close to 0, and it doesn't reflect the riskiness of this asset. Therefore, the variance formula, there's a requirement to somehow absolute the difference of between the daily returns and the mean, so that when we sum up, it is a true reflection of the riskiness of the asset. So therefore, the variance formula is as such. It's the summation of the returns per day minus the mean, which let's call it R bar. So we have to square it, okay, over number of days minus 1. So you may ask, why do we minus 1? I think it's not the intention for me to go into the in-depth why we want to do a minus 1 here, but just think of it as because we are taking a sample of the whole population, and we need an unbiased estimate of the variance of the whole population. So the denominator is always we have to less 1 from the whole sample count, so that to get the unbiased estimate of the population variance. Okay. Let's move on to the concept of covariance. And again, let's look at these two asset returns again. We can see that when there's a positive return for asset 1, there's also a positive return for asset 2. Similarly, for day 2, when there's a positive return for asset 1, there's also a positive return for asset 2, and so on and so forth. So the concept of covariance is such that we have to compare two assets and determine whether the two assets move in tandem or they move opposite of each other. Maybe it's good to introduce a third asset now. So assuming a third asset has this returns profile. Okay, so you can see the third asset is basically moving in opposite direction of the first asset here. So when this first asset has a positive return, the third asset has a negative return, and so on and so forth. So there has to be a way of linking the returns profile to assets, and this is obtainable through the covariance function, which is basically the product of the difference between the returns and the mean of two different assets. So let me write down the covariance function. Okay, so covariance function is basically let x be the one of the asset and the mean be x bar be the mean of the second asset, and yi be the second asset and y bar be the mean of the second asset. Again, we are dividing by n minus 1 because this is a variance. Covariance is a variance. So if you look at the formula, we are taking the difference on, let's say, day 1 between x and x bar. Okay, and on day 1 between y and y bar. So basically, we are saying that if they move in tandem, so these two will have the same direction, and both are, let's say, both are either both positive or one positive, one negative, or both negative. So the direction matters, and the summation of the whole series will give us the covariance number. Okay, so next, let me illustrate the concept of correlation. If you look at this number and then at this graph, okay, we can see that for the first asset, the movement around the mean is fairly small in relation to the other two assets. So but we are now multiplying something which has very small deviation against something that has a very large deviation. So in a way, even though this number makes sense, but it'll be good if we can scale the numbers down so that it's comparable against each other. So we can do it by using the concept of correlation, whereby the covariance number is being scaled down by the standard deviation of each asset. Okay, so we can take a look. We can see how it's being done here. Okay, so we scale this down by the standard deviation, which I denote by sigma x. So we scale x down by the standard deviation of x, multiplied by the same function here, the same expression here, minus y bar, over the scaling down of y using the standard deviation of y. Okay, then this whole expression divided by n minus 1 here as well. Basically, we can reduce this to covariance between x and y over the standard deviation of x, standard deviation of y. Okay, so this, in summary, is the concept of a correlation and the usefulness of correlation. So once we divide by, okay, so if you look at this function, it's basically, if you can intuitively you can think of this as the difference between the return and the mean per unit standard deviation of x. And similarly for this. So when you think of per unit, we know that this will range from -1 to 1, because we are talking about unit here. Unit times unit is a unit. So we know that correlation is a number that ranges from -1 to 1. Okay, -1 meaning that these two assets are uncorrelated. So when these two assets are negatively correlated. So when one moves up, the other one moves down in the exact magnitude. And when it's 1, both move in the same direction in the exact magnitude. Most assets are somewhere in between. Okay. Let me illustrate this in the form of Excel. So I've 3 assets here: asset X, Y, and Z. Basically, I've created this such that Y is somehow positively correlated with X and Z with negatively correlated with X. So if you can look at this graph here where I plotted the returns of X, Y, Z over time, X is given by the blue line, Y is the red line, and Z is the green line. So when X go up, Y goes up, and X goes down, Y goes down. Conversely, with comparing between X and Z, when X goes up, Z goes down. When X goes down, Z goes up. So we can tell from the graph that X and Y are positively correlated, X and Z are negatively correlated. You can use the Excel formula to find out the correlation, or you can simply use what we have done here, the tedious way, to complete the correlation. And I've done that using the Excel formula here. Correlation between X and Y is 0.85, which is really very, very close to 1. Correlation between X and Z is minus 0.7, which is, as you can see from the graph, is negatively correlated. Okay. Okay, before I talk about diversification, I want to just quickly talk about standard deviation, which is very simply the square root of variance. Because we have squared the difference between the returns and the mean return, so basically we can easily square root the whole function to obtain the standard deviation. So basically standard deviation is simply the square root of variance, which is the square root of this whole function. Okay, so let's proceed to the topic of diversification. Maybe let's start off with diversification of a portfolio where we hold 2 assets. So when we talk about diversification, we are no longer confined to investing one asset. We are investing in a portfolio of many assets. And so to start off, let's look at 2 assets. So let's say maybe we invest in this one and this one together in the same portfolio. Okay, let me clean off this thing and make space. Okay, assuming we are given $200 and we invest in asset A and asset B. So we have asset A and asset B. Okay, we invest in equal quantum in both assets. So we have $100 in asset A, $100 in asset B. So in the first day, asset A say makes 4%. Asset B makes 9%. Question is, how much did the portfolio make? Okay, we can easily do this in in a more long-winded manner by calculating the amount that asset A made during that day. So this one is basically asset A made $4, asset B made $9. In total they make $13. Okay, and the return for the day is simply 13 over 200, which is 6.5%. Okay, instead of doing this manner, we can see that we can shortcut the whole process by doing this, by taking 100 multiplied by 4% plus 100 multiplied by 9% divide by 200. Okay, this will give you 6.5, but by simplifying this, we can see that this is 100 divided by 200 is basically the weight of asset A in the portfolio multiplied by the return of asset A plus 100 divided by 200, which is the weight of asset B multiplied by the return of asset B. Okay, so this is basically portfolio return. It can be expressed as such. So this is the formula for the portfolio return. And if we're talking about 5 days or period of time, the mean of the portfolio return is simply given by summation of this whole thing, portfolio return over the period of I days, I to n days. So it's nothing much here, and of course we have the mean, and we need to obtain the variance as well, similarly to the single asset example that we went through just now. The variance of portfolio comprising of two assets is simply variance of portfolio. P denotes portfolio. It's the same formula that we use in a single asset. RP I minus RP whole thing squared over number of days minus 1. Okay, so it's exactly the same formula, except that we are talking about portfolio returns here instead of single asset return. And if we substitute this RP into here, so if you substitute this RP into here, and you substitute this term into here, we can reduce this whole formula into the weight of A multiplied by return of A multiplied by standard deviation of A, square the whole thing, plus weight of B, standard deviation of B, plus 2 times weight of A, weight of B, covariance between the returns of A and returns of B. Okay, so this is the formula that for calculating the variance of a portfolio comprising of two assets. Okay, so to illustrate diversification effect, Let us look at the Excel example. Okay, let's look at this example. We have two assets here, and the weight of each asset in the portfolio is 0.5. Standard deviation, we set it to be the same, of 0.2. So let's look at the calculation of portfolio standard deviation. I've used the formula that we illustrated earlier. Is the weight of the first asset 0.5 squared, which gives you 0.25, multiplied by the standard deviations of the first asset squared, plus the weight of the second asset squared multiplied by the standard deviation of the second asset squared, plus 2 times the weight of the first asset multiplied by the weight of the second asset multiplied by the covariance term. The covariance term is also equal to the correlation multiplied by the standard deviation of both the assets here. So I've varied the correlation in this column and calculated the portfolio standard deviation here. So we can see that comparing the portfolio standard deviation against the standard deviation of each of these assets, we can see that the portfolio standard deviation actually, the majority of the time, is smaller than the individual asset standard deviation. It can range from 0.2 when the two assets are perfectly correlated, all the way to 0 when the assets are negatively correlated. I plotted the graphs here, and which essentially showed what I've just said. So basically, this actually illustrates that the diversification effect of a portfolio containing two different assets of equal standard deviation, which actually depicts the risk reduction when we hold multiple assets. Okay, that's all I have today.